Hi, so welcome to Math150 Multivariable Calculus, Section 1, Class 2. I'm Professor Miller. We have just started with a detailed discussion on how we're going to be presenting, and we have decided to use the two blackboards and keeping the computer focused on that. This is good because the swivel device that I have been using has broken and it no longer swivels, so it is nice to be confined to just something like this. I will try to remember not to speak as I move the blackboard down because I'm going to assume that is not going to be easy to hear at home. Okay, so this is very different than hopefully classes you've taken in high school, where I am having you watch the videos before class. And doing this, 60% of your grade is a 92.5, right on the cusp of an AA-. These classes will be far more effective if you tell me what you want to do, what was confusing, what you want to discuss. So one person has already sent me some ideas to talk about, and so I'll talk about that first, and then if there are other things people want, just let me know. And again, you can speak up either live in class, or you can let me know beforehand so that I can start preparing things. So we were talking about vectors, and we were talking about notation. So notation is extremely important. It can be boring to learn, but you have to learn it and you have to be able to talk about things quickly. If you forget notation, you can always look it up. There's a lot of things that you may have seen once in your life but have probably forgotten. Directrix, anybody remember that term from Algebra 2? When you start talking about conic sections and a parabola is all points that are equidistant from a point in a line, I think the line is called the directrix. I have kids who are doing Algebra 1, Algebra 2, and geometry right now. I'm a professional mathematician. I believe I am reasonably confident. And a lot of times when I look at their stuff, I go, oh, it does have a name. Okay, there is actually a name for the horizontal line in a fraction. Does anybody know what that is called? So we can still talk about fractions without knowing what that is. As you get more complicated quantities, however, you need good names, you need good notation. Capital F for the antiderivative of little f is good notation. We use R to represent real numbers, and R to the n is R plus R n times. So these are going to be n tuples of real numbers. And so when we talk about vectors, vectors have magnitude and direction. So we often write V in Rn. Notation, as I said, is extremely important. Why am I writing the real numbers like this? I'm trying to emphasize that this is bold R. So in books, they often have R in bold. It would not be good for me to be trying to do things in bold on a blackboard with chalk. And in fact, I edited a math book a few years ago, and I had contributors from all over the world, some of the top mathematicians, and one of them was very insistent that I not use notation like this for his section, because you only use notation like this on the blackboard. In a textbook, you can use bold. So he's like, I don't want that. Perfectly fine. The goal is to be able to look at things and quickly understand what's going on. What do you think is an arrow over the V? It's a vector. To remind us, just when we're looking down, this is a vector. It's nice when you look at quantities to be able to quickly see what they are. And so vectors have magnitude and direction. And so the cultural extra credit, we've already mentioned. Which villain am I thinking of? Vector from the original Despicable Me. What are good examples of vectors? Velocity. Velocity is a great one. So it tells you how fast you're traveling and what direction you're going. So a lot of times we sometimes are a little careless. What's the magnitude of velocity? Speed. And so the magnitude of velocity is speed. This is going to be a scalar. So it's just a number. And for us, the scalars will mostly be the real numbers. Occasionally, they'll be the complex numbers. Do you like this notation? absolute value of v equals speed. This is a personal preference. You can like it or not like it. What's good about this? Are you happy?
It just gives you the absolute value, so you're not exceeding.
Well, is it the absolute value? What would be the absolute value of, let's say the vector v is in a completely non-random choice 3, 4. Okay? So here is my vector 3, 4. And so if I want to find its length, this is 3, this is 4. What a surprise, it's the Pythagorean triple 3, 4, 5. And so the way we would find the length of, say, v1, v2, that'd be the square root of v1 squared plus v2 squared. Now, if we had the absolute value of -3, that would just be 3. So this is a generalization of the absolute value. And so we're overriding the notation a little bit. When the absolute value notation was initially defined, it was defined for real numbers, or maybe complex numbers. But now we can generalize this, and if I had 3 components, v1, v2, v3, it would just be square root of v1 squared, v2 squared, v3 squared. And sometimes instead of doing 1, 2, 3, we might do v sub x, v sub y, v sub z. It doesn't really matter which we use. What's the advantage of using 1, 2, 3 over x, y, z? It's easier to tell the order. I would say we are pretty good about the order of x, y, z. Not a bad guess, but I'd say we're pretty good about the order of x, y, z. We don't run out of numbers, right? Any Dr. Seuss fans here? Wait, no Dr. You know, you're probably familiar with the Cat in the Hat. You know, the sun did not shine; it was too wet to play. I actually got into a Seuss rumble with one of my colleagues at Brown years ago, and he sadly destroyed me. But it wasn't fair because he had kids and grandkids, so he had 2 whole times of going through and learning. One of Dr. Seuss's books is On Beyond Z, when the regular alphabet just isn't enough. And he adds more letters. But it's still only finitely many letters. The advantage of using 1, 2, 3 is, well, if I want to go up to 4 dimensions, 5 dimensions, 6 dimensions, I know what to do next. Now your question about the order, you know, it's easier to tell the order. Well, if I wanted to do 4 things, would I do W, X, Y, Z, or would I do X, Y, Z, W? Or did it be different, X, Y, Z, A, and wrap around? And so it's not clear as you go into 4, what's the right way to go into build to extend on X, Y, Z. So 1, 2, 3 is much better. We often use I hat, J hat, and K hat to represent unit vectors in the x-axis, y-axis, z-axis. If we wanted to go to 4 dimensions, what would come next? L. I hate L. Why do I hate L? It looks like a 1. And so you should always write, the L in a fancy way, so that you can quickly look down and distinguish, and it's not a 1, it's an L. What number do I hate? Or what letter do I hate because it looks like a number? I'm sorry? 0. 0, because 0 can look like O. So we would never use O as a variable. What else do we try to avoid? Your handwriting might be better than mine. S is a bad letter to use because S can look like 5. So you want me to just quickly glance down. So, velocity is a great example of a vector. There's lots of other vectors we can look at. One vector is, imagine this is some portfolio. You have N companies, and this is the stock in each. And so I can tell you by giving a vector, this is how much I own each company. If you want to think of the Williams endowment, you can represent this Williams endowment as a vector. We need more though than just how much we have in each company. What do we also want? So here this is number of shares. What else might we want? Okay, a little bit more basic than just going with decreasing. Not quite right, a little bit more basic than direction. So I know how much I have in each company. What other information do I want? So I have 100 shares of we'll do Apple. We send a lot of students to Apple. We have 100 shares of Apple. Am I happy? What do I need to know? The value. So I don't want the prices. So I don't have a price tag. P1, P2. And so I have another vector that's the price of each stock. And now can I figure out how much Williams has? Yes, I can calculate how much Williams has. Does that mean if Williams says we're going to cash out today, we can take all of this money immediately? No, that is outside the scope of this class. The economic implication of Williams divesting 100% instantaneously in the market. I do not think Williams could get its entire market share if it tried to divest immediately. I don't know. But how would we figure out how much we have? It would be the dot product. So the dot product is one of the concepts we're seeing. The dot product is the sum of the products. P1, C1 plus P2, C2 plus Pn, Cn, or I can write it as the sum that goes from 1 to n of Pk, Ck. And that will tell you how much we have. And so here's a nice example of where you would actually use the dot product. You may not care about calculating the angle between vectors, but trying to figure out how much you have. Now, the comment you made earlier about the direction things are going, that could be extremely important trying to decide which stocks do we want to keep. Where do we want to invest more money? So, my father used to work in high tech, and then he was tired of the hours, he was tired of not being his own boss, he became a business broker. And one of the things he did is he helped evaluate businesses, he helped find buyers, he helped sell them. And I remember he gave me a problem when I was young, and I will give you this problem now. So imagine we have 3 people, and I can do it slightly different way. And let's say person A owns 52% of the company, person B owns 46% of the company, and person C owns 2% of the company. Okay? How much is person A worth? How much of the company does person A own? 52%. How valuable is that 52%? Let's say the company is trying to decide how to distribute profits. What might person A suggest? I'm sorry? So one is person A could be an egalitarian and say, let's split things up based on what percent you have. What is another way person A could behave? I own it! I vote we give 100% to person A. All in favor. And person A would vote aye. And person B and C would vote nay. And the ayes have it. How much is person A's stock worth? So in some sense it's worth 100%. In another sense it's worth 52%. You can make an argument One thing, of course, is eventually person A might die, and then they might send their stock to different descendants or charities or whatnot. But right now, you can make an argument that person A is worth 100%. What if instead person A falls down to 46%? And this actually happened in Heinlein's story, Drawing to Summer, where there were 3 people, and it was now 46%, 46%, 4%. I think it was actually 49, 49, 2, or 48, 48. How much is person A worth now? So why is person A worth 50%? But you also have person C. So A and B clearly have more of the companies than C. How valuable is A's 46%? Is it as valuable as the 52% a moment ago? No. How valuable is C's 4%? Very valuable. How valuable would you say C's 4% is? 100%. So you think person C controls the company by themselves?
Sometimes both are like A and B are going to apply for their any decision.
Yeah, but who? Yeah, I would actually say it's 1/3. You can look at coalitions. How many winning coalitions are there? Well, if everybody agrees, it doesn't matter. And then you only need 2 out of 3. So when you look at this, you could actually say that C is worth the same as A and B. Right now in the US Senate, how valuable is Kamala Harris's vote? If you interpret the question the right way, there's a unique answer. If you don't interpret it the right way, the way I'm thinking of, there's more than one answer. When does she vote? The vice president only votes when there is a tie. So how valuable is her vote? If she only votes when there's a tie, let's be a little bit more than very valuable. How valuable is her vote? She decides. What if she doesn't vote? Well, then if she doesn't vote, then her vote means nothing because she's not voting. So the way our system is set up, if you have party cohesion, how much is an individual vote worth right now in the House or the Senate? If the parties always vote en masse, it really doesn't matter if you're in the minority party. A lot of theory goes into voting coalitions. And they've done this in the European Union with the different countries that have merged, and how much weight does everything get? And so you could actually form vectors, and you could give weights to different things and try to assign. But I wanted to just go through this example to highlight the fact that it's not always clear how valuable something is. You always need to put things in context. And it's extremely important to make sure that that context is clear. I know firsthand that it is very easy for context to be forgotten and not to be propagated forward. But you have to look at things in context. Right now, person C is as valuable as A and B in terms of control of the company. Okay. So there's lots of different vectors that you can do. How many people have taken any physics? There's a little bit of physics. So you might have seen your center of mass. You could have a bunch of particles, and maybe the interaction of the gravity, so each one is pulling on all the others. And you have some coordinate system, and you could try to calculate the center of mass of the system. And in certain situations, the center of mass is conserved. And so what I can do is for each one of these is I can draw a vector from the origin to my point, and so on. And so I could do the center of mass vector would just be 1/4 V1 plus V4. just calculate something like this. And it turns out when you try to do some questions in physics, there are often quantities that are invariant, that do not change over time. And if something is conserved, that's wonderful. It also tells you there might be a natural coordinate system to use. So imagine the center of mass doesn't change. Where might you want to put your coordinate axes? At the center of mass, right? Because if the center of mass is not moving, it might be really good to measure everything from the center of mass. Hopefully, that's not a terrible ellipse. Hopefully you've seen equations of ellipses. And the equation of ellipsis is a, negative a, b, negative b, x over a squared plus y over b squared equals 1. Does this seem vaguely familiar from high school algebra 2? I could be evil and give you an ellipse that's not aligned with the coordinate axis. We still have ways to write down the equation of the ellipse. Linear algebra, and as a general rule in this class, if I ask what would be useful to solve this problem, as a rule of thumb, linear algebra is the answer. The next natural class after this, it teaches you good coordinate systems to use to attack problems. How many of you have done the equations of an ellipse that's not aligned with the coordinate axis? Okay. It turns out in linear algebra, it's almost as easy as this. What would you like to do to the coordinate axis? Yeah, rotate them. So instead of using the XY system, let's use the UV system. In the UV system, it's a standard ellipse. And then we just need to know how do we rotate from XY to UV. And so we can easily convert from a standard equation in UV space to an equation in the XY space. For a lot of problems, there are natural coordinate systems, there are natural directions. I am from Boston. What city do you think I despise? New York. But I have to admit that there is something New York does better than Boston. And if you say a certain thing right now, you will fail this class. Hence, I am a Red Sox fan. What does New York do better than Boston that I'm willing to admit and give them credit for? Streets. In which part of New York? The grid in Manhattan. No. It is a beautiful grid system with the streets and the avenues. It's not perfect, but it's pretty good. You compare that to Boston, where you have roads that cross each other multiple times. It's much easier to write down your coordinates here. In Manhattan, is it clear which way you want to write down your coordinate system? Yes, east, west, north, south. When we're doing vectors, we always want to ask, what is the choice of coordinate system? And for some problems, some choices are easier than others. Okay. The other comment that I was asked to talk a little bit about was about molecular dipoles in chemistry. So how many people have taken a chemistry class? There's a little bit more chemistry than physics. And so in chemistry, one of the most important compounds is water. Does anybody remember anything interesting about water? There's a lot of stuff. What do we know about water? It's polar. So what does that mean?
It has like positive and negative charge.
Okay, so water is H2O. How does the water molecule look? It's a bench shape. O. I'm trying to do this without you. It's about 109 degrees. That's right, it's been a long time. Is it not right? Or is it more than 109? I don't, I thought it was 109, I might be wrong, but it has a bent shape like this. And the other compound that I think was given was it carbon dioxide? What's the other one? I think it was carbon dioxide. And CO2 is more linear like this. And the different structure of the molecules affects how they interact and how they can stack in terms of what kind of shapes you will get, what kind of flow properties you will have. So when we're looking at this, the angle over here is extremely important between the two hydrogens. And here, I thought it was 109, maybe it's 130 something.
Okay.
Excellent, thank you. There's also beautiful angles from plants, the Fibonacci, the golden angle, which we might talk about later. This angle is 180 degrees. And because of that, it has very different properties in terms of how it interacts. So I can quickly look at angle one.
105.
105, okay. That wasn't too bad. It was within 5%. Okay. So this is another example of why we care so much about these vectors and about these angles. It's going to impact the chemical properties. And when you have something nice and linear like this, in terms of the magnetic field, the electric field it's going to create, it's going to be very different than something like this in terms of how things can be protected. Like charges repel, opposite charges attract. And it's going to give you very different structure in terms of how things can be coming together. This is another reason why we care so much about this. The last little bit is on notation. So what is cosecant of theta? Who remembers the trick? Yes. It's not in my top 10, but if I could change things in the world, this is on the list. What would you define cosecant to be? I would define it to be one of a cosine as well. I would have the cosine and the cosecant go together and the sine and the secant go together. You have to be careful about notation. If you do different subjects, if you do math and physics, in one we sometimes rotate the coordinate axes, and the other we rotate the points. So the rotations could be off by a factor of -1 in terms of how the equations look. In terms of three-dimensional spherical coordinates, the physicists and the mathematicians have slightly different notation as to which is theta and which is phi. I learned it from the physics department first before the math department, so I still have to remind myself, oh, I am teaching in the math department, I have to use the math notation, which is better. It's better notation, but I learned the physics notation first, and that's what was just hardwired in. Speaking of, one of the things I strongly urge all of you to do is learn how to do some basic programming. This is the 21st century. You have so many programs mathematically is wonderful. They can plot things for you, they can run simple code, that you can investigate things and build up some intuition. And I'm happy to use some class time to just talk to you about how do you do some simple programming to build up some skills. Okay. So these were the questions people had asked me to cover. We still have plenty of class time. Are there any other things people want to talk about? I will erase what people think for a moment. So one of the big things we saw about vectors is calculating their length. And And this is the power of the Pythagorean theorem. We initially proved Pythagorean theorem in the plane, but you can actually generalize it to 3, 4, 5, 6 dimensions by just taking triangles and triangles and triangles and projecting down. And so this is going to be one of the most fundamental important options. Any other questions on the things we have done? I'll be watching the chat and taking these steps. Yes.
I'm wondering whether you mentioned the Dipoles in their work, because they were relevant structures for this type of
They can be related to vectors, absolutely. But you can represent things, especially if you have multiple objects. Right now we were doing the simple case of just one company. What would happen if you had somebody who had shares in multiple companies and you're trying to figure out just how much power they have? Or you might have votes that only come into play at certain times. Like, how valuable is the vice president's vote? I don't want to go into details. I had a misunderstanding with one of my lab professors at Yale, and I was told I was going to be penalized, but only if it affects my final grade. How can you interpret that? So if it will lower your final grade, I will give you the penalty, but if it won't lower your final grade, I won't give you the penalty. Have I been penalized? I would say so. And so when you're trying to figure out how much things are worth, your content really matters. And so a lot of times you'll have conditional situations, which makes things far more interesting and far more complicated. If we have very pure things, just one vote, that's a lot easier to analyze. We don't necessarily need the power of vectors. But as we go further, and you're trying to figure out how powerful is somebody, and you have many different things going on simultaneously, you want to come up with some kind of weight for that person. Maybe they sit on certain committees as well. Or maybe for some things, I serve on a regional school committee, there are some things where you just need a majority of people to support. There are other things where you need to have at least one member. We have 2 towns in the district, at least one member from each town voting in favor. And I know there was a problem in the school district next to us a few years ago where they wanted to close one of the schools, and they needed just a majority of people to close. And so the 3 people from the town of the elementary school that was going to be closed all voted no. The 4 people from the other town all voted yes, and the motion passed 4-3, with not one person from the town who wanted the school, who had the school wanting it closed. And so this is meant to be, a simple introduction to an incredibly rich topic. Any other, questions on specific materials? We have Pythagorean theorem, we have vectors, we have dot products. We will prove the dot product formula, I think, in the next lecture. All right, so with the remainder of the time, I would like to use this to try to review some stuff from Calculus 1 to Calculus 2. I know it's been a while since people have done that. And I want to do things, again, I kind of like to imagine myself as the Almighty with complete control over the universe. You may feel free to envision yourself similarly. If you could decide what the product rule would be for calculus, what would the derivative of a product be? I'm sorry?
Like if you were to differentiate f into
Yes, the derivative of a product would be?
f prime x times g.
Yes, the product of the derivatives, right? And the derivative of a quotient would be the quotient of the derivatives. Right? That's not the case. If we have a of x is f of x, g of x, then what is a prime of x? Wait, what did you say?
I said f of x times the derivative of g of x plus g of x times the derivative of x.
So you're not wrong, but most people would do it the other way. So it's not wrong. Most people do f prime of x, g of x plus f of x, g prime of x. It is perfectly fine to do them in either order. But normally they do f prime g plus f g prime. The proof is not too bad. And the proof uses one of the most powerful techniques in mathematics. doing nothing. There are two ways we can really do nothing in mathematics. Anybody know how we can do nothing? Add zero. Adding zero is a great way to do nothing. How else can you do nothing? Multiply by one. And then my professor Peter Jones said, actually, the log of 1 is 0, so there's really only one way you can do nothing like that. I'm not going to go through the proof of this. Instead, what I want to do is I want to convince you that this is reasonable, and I want to show you how you can experimentally conjecture this. That's more useful than actually doing the proof and doing the algebra. How can we sniff out that something like this might be true? Well, we need to start off with functions f, g, and a, where we know f prime, g prime, and a prime. Can you give me a simple function whose derivative you know? X squared, what else? X cubed, what else? More generally.
Oh, more generally.
Yeah, more generally, we have x squared, we have x cubed. More generally, we have x to the n. So let's let f of x be x to the n. G of x will be x to the m. And so a of x is just x to the n plus n. And again, x to the n is one of the easiest functions to differentiate. This is the binomial theorem. X plus h to the n minus x to the n over h. What's the derivative of x to the n?
And
And the derivative of g of x. And I should probably do one a prime of x is n plus m, x to the n plus m minus 1. So now that we have all of this together, can we find a way to express a prime as some function of f, g, f prime, and g prime? Well, I need to get up to x to the n plus m minus 1. When I look at this, oh, look, I have an x to the n and an x to the n minus 1. If I multiply these two together, that does give me something with the power x to the n plus m minus 1. And if I multiply these together, doing it this way, your expression of doing f g prime first is the right way to do it. So for this argument, writing it this way, it is more natural to say f g prime plus f prime g. You're keeping the order of f and g together. So sometimes the way we write things is actually indicating how we got there. So when we look at this, it suggests maybe f prime of x is f prime of x, I'll do you, f of x, g prime of x, plus f prime of x, g of x. Is this a proof? No. What's 16 over 64 in lowest terms? 1/4. That was terrible how long that took. 19 over 95. All right, that's better. That's better. 12 over 24. That was a little slow. Let's do one more. 49 over 98. One of the answers is wrong. I claim that's wrong. I think it's 1/4. You agree it's 1/4, right? Yeah. 16 over 64. Well, you clearly cancel the 6's diagonally. You get 1/4. 19 over 95. You clearly cancel the 9's. You get 1/5. 49 over 98. Cancel the 9's. You get 4x, which is 1/2. So you have two-digit numbers and you're dividing them, and the opposite diagonal is the same, you cancel that, and so 12 over 24 should really be 1/4. Okay, I think we all agree 12 over 24 is not 1/4. This is the danger of looking at small cases. If you look at just a few points, you can easily be misled as to what's going on. So over here, does this give us some confidence that this could be true? Absolutely. But maybe this function is too simple. So then the question becomes, do we know any other functions and their derivatives? So we have to know both f, g, and f times g. So what's another function whose derivative we know? Natural log of x, so we could try to do that, but then you would have to know directly the natural log times something. And that's what's going to get hard. There is another function that's nice. So there is the exponential, but then you would have to know directly the product of an exponential with something. And unless you have two different exponentials, and you could do either the 2x and either the 5x maybe, but you want to be very careful that you're not using the product. So what other functions do we know? Okay, sine and cosine. F of x is sine of x. G of x is cosine of x. A of x is sine x, cosine of x. Does anybody know how you can simplify sine x, cosine x? I'll multiply by 1. It's 1/2 2 sine x, cosine x. Anybody remember 2 sine x, cosine x? It is 1/2 the sine of 2x. So again, what am I doing right now? I'm showing you how to experimentally conjecture. That's a valuable skill. At the same time, I'm reviewing calculus without just saying, all right, now we're going to review material you should already know. This is a more enjoyable way, at least for me, to talk about the things you should have seen. So now, what's the derivative of sine? Cosine. And it's only true in radians. It's a great lecture as to why that's true. We will talk about that later. What's the derivative of cosine? And so this is the mnemonic I like to remember. There's a minus sign that you have to remember. Where does it go? Does the minus sign go with the derivative of sine, or does it go with the derivative of cosine? Minus sign, minus sign. That's how you can hopefully remember where to put it. What's the derivative of a? A time of x is going to be 1/2. The derivative of sine is going to be cosine of 2x. And then we have the derivative of 2x, which is 2. And so we've used the chain rule. Well, we've used the chain rule in a very special case where we've just increased our speed going through things by 2. So it's reasonable that we increase the derivative by 2. We're going through twice as fast. We could actually prove this directly. We don't need the full strength of the chain rule. All right, now the fun begins. Let's look at f prime g plus fg prime. So f prime g plus fg prime. All right, cosine times cosine, that's cosine squared x, minus sine squared x. Does anybody remember what cosine squared minus sine squared is? If you look at the board, there's only one thing it can do. What does it have to equal? It has to be cosine of 2x. This is just cosine of 2x here. If the product rule is to hold, it has to be cosine of 2x. This is one of the problems with trig, is that you have different expressions that are the same quantity, and they look different, but they are the same. Cosine squared minus sine squared is the same as cosine of 2x. You could use sine squared plus cosine squared as 1, sine squared is 1 minus cosine squared. This is the same as 2 cosine squared of x minus 1. That's another way to write this. You have all of these different relations for these quantities. But if you happen to remember your trigonometry, if you happen to remember your angle addition formulas, and the proof is not terrible, if I assume that this is x and this is y, and I want to prove the formula for the cosine of x plus y, so that's just finding this length dropping down. And one of the ways you do this is you just keep drawing auxiliary right triangles, touching things like this. And then I will have a line coming from here over here as well, making another triangle here. This length here is this length plus this length is the same as this. If you look at this, if this is 1, this length here is cosine y, this is sine of y. So this length here is just the sine of y. If this angle is x, what's this angle over here? 90 minus x, right? So what would this angle be over here? That would be x again. So this would be 90 minus x. So this would be x over here. So this length over here would be hypotenuse times the adjacent side, right? Cosine of theta is adjacent over hypotenuse. So this length here is just sine of y cosine of x. And so if I'm trying to calculate the sine of x plus y, which is this quantity here, you can see, oh, here's the first piece. The second piece, I want this length over here. Well, this line over here is 1. This length here is going to be cosine of y. I then take the sine to get that. So this piece here is going to be cosine y sine of x. My entire height, sine x cosine y plus cosine x sine y. That's the sine of x plus y. You can get the cosine of x plus y the same way. So this is a way to quickly review some of the trigonometry. I'm not going to require you to know your trig identity. The more you know, the easier it is. At some point in the semester, I will show you how to derive every trig identity by knowing the exponential. It turns out the exponential function and the trig functions are related. Do you feel more confident now about the product rule? It didn't just work for x to the n, x to the m. It worked for sine and cosine. Does that give you more confidence? Yeah, this is a much harder example. And the solution as to why they're equal now involves a trig identity. So I feel a lot more confident. All right, so again, this is a chance for you to assess how the class is going. This has been the first real lecture now. And my goal is to have classes like this, so that you watch the video, and then if there are things that you want me to discuss in greater detail, if there are applications, let me know and I will work that in. And then the rest of the time, I will use to just go over problems. If you want me to do problems from the section, say, hey, Professor Lewis, can you do these problems? And just let me know in advance so I don't have to load the heavy books with me. Otherwise, I'll try to do stuff like this and try to review stuff from calculus that you should have seen. And will hopefully now make a little bit more sense. All right. Have a great day.